and I mean, whenever you have doubts, and it would be more or less an interactive session. So I think I'll give the platform to Professor Sergey to, I think it's fine to ask questions, right?
Yeah.
In between, yeah.
Yeah.
So, and then you can continue if you have further question over coffee. Okay, Sergey, please.
Great, thank you very much. 1:30, excellent. Now we can start. So yeah, as you said, we can do either way. We can also, you guys can ask questions in the end, or if something isn't clear and you need an immediate clarification, we can do it. So again, thank you for the organizers. I'm very happy to be here. So my task is to talk to you about quantum machine learning today. My name is Sergey Gleyzer. I'm a faculty at the University of Alabama. And I'm a particle physicist by training. I do a lot of AI, also quantum as well. Okay, first of all, I would like to wish you all a happy holiday. If you're in US, it's Happy Independence Day. If you're a physicist, it's a Happy Higgs Discovery Day, right? So let's congratulate ourselves again for this nice holiday that we all can celebrate, right? And in fact, I'll give it even another, I call it Higgs Dependence Day, right? So it's kind of a mix of Higgs and independence, right? All right, but now coming back to what we're going to do today, we're going to talk about quantum machine learning. In fact, I'm going to do something a little bit different compared to some of the other lectures, in that I would like to spend about an equal time between theory and practice, because just as is in machine learning, you can hear all the theory you want. It's all going to sound great until you go and do it and program your actual model. You know, you're not going to be able to do anything. And I would like you guys at the end of this to be able to go home, wherever you are, and go and program a quantum machine learning model, okay? So that's going to be the goal at the end of the 4 lectures. So what we're going to do is today, the first one, we're going to focus more on theory, all right? Later today, in the afternoon, we're going to start with the practical. And then we're going to do a similar thing on Thursday, where we're going to split time between the theory, because we all need to, you know, kind of get ourselves up to speed on what this is about. And then the real goal will be, right, to program a quantum circuit, right? That's our real goal for my lectures, okay? And we know what we're doing, and we're going to do this using Jupyter Notebooks. How many of you have already used Jupyter Notebooks? Many hands. Very good. Very convenient. You'll have a fun time if you haven't done this. All right. So what's a quantum circuit? I'll tell you in a little bit. All right. But by the end of this school, you'll know how to do this. Now, I would like you on the theory side to understand the basics of QML. Now, when you talk about quantum machine learning compared to machine learning, so it's a new field, okay? It's only been around like 5-6 years in reality, okay? So now a lot of machine learning people go around, QML, this is interesting. And then statistics, is all foundation of both, they kind of look at and say, hey guys, what's going on here, right? So the point is that we're going to learn today. I'm going to try to connect to ML, since you've just learned, many of you have learned many good concepts, very good lectures earlier today, right? Ramon and others, of course, and I'll build upon that, okay? So I'm not going to start from complete zero in machine learning, but I'll connect to all the things you've heard today and yesterday, and I'll introduce whatever you might need on the quantum side, and then, statistics. Hopefully you know already a little bit about it. Okay, now, sorry, I keep getting this wrong. Let's start with basics, right? In order for us to be able to do this, we need to talk about basics of quantum computing and also some basics of machine learning. So I'm just going to quickly go through this. You should already know most of this stuff by now on the machine learning side. But I like this quote, Herbert Simon: learning is a process where your system, whatever it is, improves its performance based on experience. So I like this definition of machine learning, and this can extend also eventually to quantum. It's certain types of algorithms that can get better at a particular task with experience, and the kind of tasks we have are, identifying cats and dogs, but if you're a physicist, maybe Higgs bosons, dark matter, right? Whatever floats your boat. So that's what we're going to start with. It's really useful when we can't really explain our expertise or there's no good solution. It's particularly useful if the model requires significant fine-tuning. And here is a key part: when your environment is fluctuating. Now, why am I highlighting that, right? Because we're going to be talking about quantum systems, and that's a little bit of a different environment than we're all used to. So it's also a very, very interesting situation. And obviously, it's useful whenever your software or algorithm is actually too complex to write by hand. So you need some automation to arrive at those solutions. Now, sorry, I'm going to keep going back because this button is in the wrong place for me. But anyway, sorry. Now, what are some good tasks for machine learning? Identifying patterns, pattern recognition. You've heard about today and yesterday about generative models and generative patterns, recognizing anomalies, anomaly detection, as you heard from Ramon, how to make predictions and forecasting. You didn't talk much about that, but that's something that is also a very good task. So in computer science, in pure computer science, in different areas such as natural language processing, speech recognition, and computer vision, it's already the way of doing things. It's the best way of doing things right now. And it's spread like wildfire because the algorithms have gotten better. And also we're collecting a whole lot of data, and sensors are everywhere. So we have very much data that we can learn from. And this certainly connects to quantum as well, because our algorithms have improved. It used to be that it was all theoretical, but now, since about 2019, we actually have hardware that works, quantum computers that we can access through the cloud. Okay, so that means that we can also be practical. And ultimately, we want to be practical. We want to solve practical problems. And this is where, in particular, quantum machine learning steps in to help classical machine learning to solve some difficult problems in a different way. Okay, that's the motivation. Now, sample applications, there are many. You can write like 10 pages of this, but I'm going to broadly focus on science, okay, since we're scientists. Some basic examples, of course, this is more related to machine learning, is computer vision, right? So whenever you have an image like this, which is a two-dimensional representation of pixels, right, a regular grid of some brightness, intensity, and the goal might be to identify different person, dog, chair, whatever. Of course, with self-driving cars running around, they need to know what's going on. So whether LiDAR or whatever other technology, you collect information of the world around you, and then you can make decisions. You need to make decisions whether there is a pedestrian or a bike coming your way. And sort of a canonical example, which you have hopefully already encountered in your study of machine learning, is MNIST, recognizing handwritten characters. All right, this is certainly an example where there are as many handwritings as there are people in the world, and therefore you can get confusion. Even people can make mistakes when writing, when trying to recognize a 2 from a 3. Depends who wrote it. Turns out machine learning algorithms can supersede human, achieve so-called, superhuman experience in this particular task. So what are the key machine learning concepts, right? And how are we going to look at this stuff? So one key concept is how to represent your data. Okay, you don't think about it very much often until you have to think about what's the right machine learning algorithm for my problem. Well, that really depends. What's your data? How is it represented? Okay, and how do you match that representation with a model? How do you pick the right model for that data? That turns out to be very relevant for both classical and machine learning. So representation or encoding, okay, is another word we're going to use. Specific model-specific components, like computational components. For example, in neural networks, there are neurons and layers and decision trees, right? You've got decisions and nodes and things like that, right? And so there are different computational components and different, what at least at first glance, seem different algorithms. It turns out there are very deep connections between different machine learning algorithms that people over time have found. For example, between neural networks and support vector machines and so on. There are different connections between these different things that are very interesting. Even though they all organically developed, that's what makes this really a science, or so-called data science. Now, the point is that there are these different specific computational components, and we can study those, and how do you build these algorithms, right, as a whole area of machine learning. And then you can abstract from that the learning algorithm. Okay, how does this algorithm actually improve its performance? How, right? You can abstract that out. And of course, the part of which is optimization, right? How does that actually happen? How do you achieve better, how do you, end up minimizing your functions and so on? So this deals with loss functions, stochastic gradient descent, and so forth. Ultimately, in practice, you have to train your models and you have to apply them at inference, right? So those are all important things in classical machine learning. Now, let's think about quantum machine learning, all right? Let's draw a parallel, and we're going to try to do this today. We're going to draw as many parallels and try to see if we can go from classical, how can we motivate some of these ideas in quantum machine learning wherever possible from things you already have seen in classical machine learning. It will require us to introduce some new ideas too, so we won't be able to just get away with parallels. But let's start there. So first parallel, and that's a key quantum machine learning concept, is data representation. Because we're going to be dealing with quantum devices, we have to represent the data, right, in a different way. We'll talk about that in a moment. We'll talk about, what else are we going to talk about? We're going to talk about this idea of quantum circuits, right, which are actually variational circuits, which connect to topics you've seen today and yesterday, right, in Ramon's lectures in particular. And how do you learn, right? How can you learn using this quantum circuit? How does that work? What's a quantum node? What's a hybrid quantum and classical system? Because in fact, most of these systems are hybrid. Why? Which part is classical, which one is quantum, is what we're going to delve into. And finally, we're going to abstract from that the learning algorithm and optimization, just as we did in the classical machine learning approach. Okay? So that sort of sets the stage for how we're going to go about it. Now, let's look at the very first thing, data representation. So we know different data types. Audio, right? You can think of these as waveforms, right? Waveform heights, one-dimensional vector, right? That can be your input space. Now, suppose you're dealing with something like an image, right? Which is a two-dimensional object, right? And now we got these intensities, right? Now there are two indices here, which means that this is a matrix where every pixel, okay, has some sort of a value, okay, between, some minimum and maximum. If you're a MNIST, 0 to 55, all that stuff. And it corresponds to the intensity of the pixel. And the goal might be to analyze this matrix and figure out some features, figure out maybe if there is a car, an object of certain type, do something like image segmentation. There are many different things you do in machine learning. But the main point is the data itself is represented as a matrix. And there are certain algorithms in machine learning, which you have heard about today and yesterday, for example, like convolutional neural networks that operate well with these two-dimensional data. Okay, there's different algorithms that operate on one-dimensional data. Or maybe you can have one-dimensional convolutions as well. So the point is that you match the model to your data in order for things to work the best. That's the idea. So continuing on, there are other types of data. Think of video. What's a video? It's a sequence of images. So now you've got images, and now you have sequences. Okay, think of like stock data or some other thing, time series data, things that you get from the sensors. So you've got sequences. Then, and there are algorithms that work well with sequences. Recurrent algorithms, LSTMs, certain types of transformers, and so on. That you've heard, some of them have been already mentioned. There, also, you can represent your data in a point cloud. Now, when is this a good idea? It's a good idea when your data doesn't have necessarily a regular Euclidean, let's say, representation. All right? Let's say your pixels have different sizes. Okay, so you don't have an easy way to make a grid, and not all data live in this Euclidean space. So it may be advantageous to actually represent it as a point cloud. And there are certain algorithms, machine learning algorithms, that work very well on point clouds, right? You can represent pretty much any data. Well, you can actually turn any neural network, for example, into a graph, right? And then you can use graph neural networks and graph ideas, graph structure, and so on to operate efficiently on those types of data. Okay, so main message: how you represent your data affects what's going to be the right solution in the right machine learning algorithm for this task. Right. Now let's go and take one more step. And this next step we're going to talk about general compute model. Okay, classical at first. So the classical compute model consists of inputs, right? And our inputs in classical computers are what? Bits, right? 0 and 1, binary, Boolean. That's why all these operations happening inside of our computers and so on, you have these gates, right? And, or, and all these different things. And the input is a bit, right? Your output is a Boolean, right? And you can build all these fancy circuits that sit inside your phone and do all the nice things you need them to do. Okay, that's our classical gate compute model that modern computer, all the computers have been always built on. So what is really interesting is that this is a classical model, and now we're going to go into a more expressive model, a quantum model, computing model. And for this, let's introduce a new concept, right? And by the way, you can express any Boolean function, right? You can decompose it into a bunch of these gates. In particular, and, or, and not is all you need to do it. Now let's talk about the quantum part of this. So you can construct a circuit from this in the classical sense. We can do the same thing in the quantum. So let's sort of start. I'm gonna write over here. Hopefully you all can see. So I'm going to introduce, the first thing we're going to introduce is a two-level quantum state called a qubit. How many of you heard of a qubit? A few? Okay, very good. So what's a qubit, right? So let's introduce some notation. This is a quantum state. All right. So we can express a quantum state, also known as a wave function, right? And very simply, right, we can generalize this as a column vector. Now these guys here, these coefficients, these are complex amplitudes. This is not real number, it's a complex number. So you can think of this as a complex probability amplitude. Okay? Now we're going to call this thing a ket using bracket notation, right? So there's a bra and a ket, while bra is this way. And in fact, it's a row vector. In fact, now you have to take complex conjugates, right? Remember, these are real values. There's complex values. There's a real and complex part. Okay, a conjugate. So now we can have our bracket notation in quantum mechanics. Hopefully all of you are familiar with some quantum mechanics, but this is basically bracket notation. So this is a ket, is a quantum state. So what's going to happen is you can express this, right, in a basis, in a common basis, as here's one amplitude of two states. There is the 0 state, and there is the 1 state. And you can think of these as, right now this is a wave function, right? We set up a state, and suppose you want to make an observation. What's going to happen is you're going to collapse the wave function, right? And it's going to collapse to one of these states, for example, 0, and the probability of that is going to be a squared. Well, modulo squared. Right? So we take the squared, and similarly, for one state, is going to be b squared, right? So observation means collapsing the wave function. Now, you can look at this guy right here, the 0 state. Each of them is a state. Okay, each of them is a state. So this particular state, you can write it down as, this is just notation, 1, 0, right? And this right here is 0, 1, 1, 0, right? So you can think of these as vectors. So a single qubit, right, these are single qubits right here. So it's a two-state system. And a nice way to represent this is using something called a block sphere. Oh, one thing I forgot to mention. Now, these complex probability amplitudes, there is a constraint, all right? And there is a constraint, of course, as you can imagine, our constraint is that the square root of these squares is 1. Right? So otherwise, this is known as the L2 norm, which if you study your machine learning loss functions, you should know that when you look at your mean squared error, for example, right, you're talking about this L2 norm. So this is essentially the same norm. So one nice way to represent this is on a block sphere, which you can see, for example, the two of your basis states, 0 and the 1, the two kets, right, are at the opposite poles over here. Okay? And what happens now is that you can pretty much put all the possible wave functions, right? All the qubit states are going to be living on the surface of the block sphere. Because of our constraint, they have to be on the surface, right? That's a so-called pure state. And because in reality, right, in real quantum systems, we have a fluctuating environment, right? There's decoherence. And so you have these things called mixed states, in which case you may be living not only on the surface, but somewhere within the block sphere. But let's leave that alone for now. So the block sphere is sort of a nice visualization. Now, why is it nice? Because now when we apply gates, it's an actual operation on the block sphere. So we'll be doing things like rotation, by an angle around a certain axis, and so on. We're going to be you can think of these different gates as operations that are going to transform one quantum state into another quantum state through some kind of an operation, right? But you can still think of that as gates, except now these are quantum gates, because now they're operating on your quantum system, on the quantum state, right? So one thing to note that these are unitary operations, and that are going to transform these states. So that's one thing, they're unitary, so that's a nice property. The second thing is that these are, you can think of this as, let's write it down here. Yeah. So if I'm talking about a quantum gate, one thing that I want to mention is that it's an operation, right, on my quantum state, my wave function. Now this right here is a matrix. That's a vector. And I'm going to obtain another, let's say some other quantum state, which is also a vector. So what's important is that this U right there is a matrix. So they're going to be matrices that operate on vector space. So if I have a 1 qubit, then normally this is a 2 by 2 matrix, right? Because qubit has 2 elements, right? Now, if I have a 2 qubit space, now it's a 4 by 4. If it's a 3 qubit, 8 by 8, and so on. Any questions so far? So far, so good? All right. Now, let's talk about a few important ideas here. Now, first idea that I want to talk about is going to be the different kinds of gates that we might have. All right. So, for instance, there is a set of Pauli gates. Now these guys right here, you can see them on the left. Oops, sorry. I went back. What do? They rotate our state, okay, by an angle, pi, around a particular axis. Okay, X, Y, or Z. Those are the three common. There is another, but these are three of them, X and Y. So whenever you see, this is the notation, quantum gate notation. So when you look at quantum circuits, they have different components. This is what they mean. Anytime you see a Z, it means it's a Pauli Z gate. Okay, rotation by pi around the Z, and so on, on the block sphere. There's other gates, such as Hadamard. Okay, notice it's a 2 by 2, right? Same as this. This is all single qubit gates, 2 by 2, single qubit operation. Hadamard is also a single qubit operation. Now, right here, we get into multiple qubit gates, in particular 2 qubit gate, and that's a CNOT, controlled NOT. So what does this thing do? Notice you have these two lines. Each of them is for, your 2 qubits. And now you'll see here there was only one. You'll notice that they're connected, and you notice this is kind of a control. Control means, so what does the CNOT do, right? It flips your second qubit to, suppose it was 0, you flip it to 1, or if it was 1, you flip it to 0. If your control qubit, so-called control qubit, is equal to 1. Okay, so based on the value of the control qubit, you're going to flip the target qubit. That's what it does. It's a really important gate. And we're going to use it, in fact, for multiple operations. So that's the very first thing to know. These are sort of really common gates. Now, I want to talk about one important thing now, tensor products. Because what we have here are tensor products, or Kronecker products as known. So suppose we have a state A, defined as usual. Let's call it A0 and A1. And suppose we have a state B, B0, and B1. So whenever we want to make a tensor product, A, B, we can shorthand that as AB. And what that is going to equal to, right, you're going to multiply these out. So there's going to be A0, B0, A0, B1, A1, B0, A1, B1. So this is the very basic tensor product, as opposed to like scalar products, right? So when we looked at, for example, like measurement, we're going to talk about measurement in bracket notation. There, when you put the two things together, you're going to get a scalar. In this case, this is a tensor product of 2 vectors, right? So you're going to get another vector. So let's just sort of look at an example of this. So suppose we look at the 0, 1. Let's look at maybe 0, 0, 1 state, right? Tensor product, 0 and 1, 0, 1. And if we multiply these out, that's going to be 0, 1, 0, 0. That's the only one that's going to survive. 0, 0, on the other hand, is going to be what? Who knows what 0, 0 is going to be? Anybody want to take a guess? So 0, 0. It's going to be a vector, right? And where is the 1? Top? Yep, correct. Right? It's the only one that survives because that's going to be A0, B0. Got it? Yeah. So you can basically cycle through all these different things. So what are these? These are basis states now for this 2-qubit system that we're talking about. Okay? These are the orthogonal bases, as we did in a single qubit, right? Orthogonal bases. These are going to be the basis vectors. So normally that's expressed as a tensor product. All right. Now, can we express everything as tensor products? Turns out, no. And that's where things start to get really interesting in the quantum world compared to the classical world. There are certain things that happen in the quantum world that you may be familiar with, such as interference, right? And these sort of cross terms can cancel out, and you may get interference. And there is another very nice thing, right, which you may have heard about, such as entanglement. Special states called entangled states. And what is so special? They cannot be expressed as a tensor product of other states. Okay? And the example of this is one well-known state, some call the Bell state. There's not just one, but this is one of them, 5+. And you can, it's basically 2, 0, right? It's the 0, 0, 1, 1, and some normalization. So this guy right here cannot, provably, cannot be expressed as a product of states. And how do we achieve this entangled state? Now remember about entanglement, right? You can achieve this in a physical system. People have achieved this in the physical system. So think of these as like, Pauli exclusion principles when it comes to electrons in an atom, right? You move one far away, you know what the other one has to be still. Similar things you can do with, entanglement with other systems, photons and so on, bosons and whatever. Now, the key thing here is that to get this particular Bell state, we can take this 2-qubit system. Usually, by default, they're usually initialized to a 0 state, right? That's the usual configuration. And you can get there by applying the Hadamard gate that we just learned, okay? And a C-naught. So a combination of those two, this control knot, is what is going to get us into this entangled state. Right? So we can actually, these are not very complicated operations, we can program quantum computers of today to get in those states. And there's a lot of expressiveness that we can achieve in that way. Well, with this, is there a way to extend this to more qubits? And certainly the answer is yes. As you'll find out in our exercise later on today, there is this very nice state called the GHZ state. The pronunciation of, I'll leave it to you to internally pronounce the full name of the state, but it's an extension of the Bell state to 3 qubits. So it's basically you add another 0 and a 1 on both sides, and that right here is a 3-qubit version of that, a tangled 3-qubit version. Okay, so this is all great. How do we measure this, right? How do you know how entangled things are? And that's now we're going to come back and think about statistics and information theory, because as you have heard already earlier today and yesterday, there's this nice concept of entropy, right? From information theory, Claude Shannon, there's Shannon entropy, there's different types of entropies defined. Now, what is that? It tells you how much uncertainty you have in your data, how impure it might be or pure. And if you have completely homogeneous data sample, your entropy is 0. Any other situation is P log P, right, minus sign. And what is nice about this is that it's a useful measure of entanglement, because you can use it to tell you where, how pure your state is or not. Pure state, entropy 0, okay? And the more states you have, now you can also define this for things like mixed states and so on. So it's a good concept also for entanglement. Now let's talk about how do we take our data. Let's say we have classical data. I'm going to leave quantum data aside for the moment. Let's talk about classical data. How can we encode this thing in a quantum state if we're going to use this approach? Well, there are 2 main ideas. One is called amplitude encoding, and the other one is called angle encoding. And the idea is that you take your classical data vector and you make it an amplitude of a quantum state. Okay, so that's one way you can do it. The angle encoding is you take the classical data and the value of your classical data vector, those vector values that you have, xi's, it determines the angle of the rotation of the gate. In this scheme, you can take any classical data that you want and put it in a quantum state. Now, what if I'm solving a quantum problem and my data is already in a quantum state? Well, there you go. No need to think about, data encoding. But for the most part, in order to use, these ideas and quantum circuits and things we're going to introduce in a moment, the very first and very important step is to encode your data onto a quantum state on which we're going to be able to operate, apply quantum gates, and so on and so on. So these are sort of the general two approaches. So let's maybe just to kind of define this a little bit more. I don't know if you can see this down here. Maybe I'm going to switch it again. And I'm going to go over here. So the main idea here is in the amplitude encoding, I'm going to call it, well, they're both A's, so amplitude encoding, right? And this is the idea where I'm going to take my classical vector, right? And now I'm going to turn this thing into a quantum vector, so there's a bunch of them. And I'm going to use the xi's amplitudes, right? Complex probability amplitudes, right? I'm going to use the classical vector to determine those values. That's how it's going to look like. That's called amplitude encoding. Now, angle encoding, as we said, we need rotations. So the same thing, right? So these are now going to be rotations of xi. Okay, I'll put this here. And this right here is going to be an operation, a rotation operation on my state, basically. So how much I rotate is dependent on the value of that vector, of the input classical vector. Okay, so now I can put it on my block sphere. I can put all those different points in different places based on where you are in the classical space. So that's the conversion. So another useful concept that we're going to need is going to be measurement. So we talked about measurement already, but it's a key thing because we mentioned collapse of the wave function, right? Usually we, when we take the observation, right, we want to, it's a scalar product, it's going to be a number because it's going to collapse into a particular state, one of our states. So because these are probabilistic predictions, you need to sample these. So there is a so-called measurement gate right here, which we're going to need because we can't directly observe the quantum state. Now, okay, a little bit later, we're going to talk about simulations and why we may have access to the quantum state as we're programming these different things and the amplitudes and so on. In real life, you don't. So for this reason, in real life, a quantum system is an open system. A realistic quantum computer is an open system at the moment, which means it interacts with the environment. It's not completely isolated, which means it loses coherence. Anytime you start with a state, you wait a little bit, it loses coherence because now it becomes entangled with the environment. Okay? Now that's why you need error corrections. And these error corrections, they're going to affect what you get. So the main point is that we're going to be using measurements anytime we want to get out of our quantum part of our system, okay? And we're going to go to the classical. So we're going to basically measure and collapse the wave function. So, by the way, one important notation, one line, qubit, quantum, two, classical. So you start on the quantum side, you end up on the classical side. Okay? So now you should be able to read quantum circuits, right? This is pretty much all you need. These are all the different gates we saw. There are more, but this is just the basic ideas. Now, I'm going to take a step back, and I'm going to go back and talk a little bit about on the classical side, principle, machine learning side. Now, the approach is usually you take your training data, right? You have a vector, you have an input vector X, you have your output Y. Now you're trying to find a mapping between X's and Y, right? You want to find a function which is going to be under some kind of a constraint normally, constraint function. So the way this looks like, this function space, these functions, these models, can be different models, right? Now they have tunable, they have tunable parameters, W, weights or whatever, things that you can modify. theta. And so the main point is that these right here, you can adjust. And your goal is to minimize something called the empirical risk function, which is using this constraint, okay, that you want it to be as close as possible to the target label. So that's how you can define a loss function or a cost function, which tells you how far you are from there, maybe under some additional constraint, regularization. And the main point is that this thing is empirical. It's not exact. Because our goal is to generalize, right? This is an empirical process because in the end, we're not going to apply this to our training data. We wanted to generalize this to another part of the data that we don't see, that the model doesn't see. You want it to work. That's why it's not exact risk. It's an empirical risk. That's the general setup of the problem. And the loss function, what does it do? It measures your mistakes, the cost of making mistakes. Okay? So this part is still we're going to treat in a similar way also in the quantum side. Now, many methods, many classical methods, it doesn't matter what they are, neural networks, decision trees, and so on, many of them use certain types of loss functions. There's different types, but commonly you find quadratic loss, mean squared error, etc., right, which is basically the difference between your target, right, and your prediction squared, and then you're going to go ahead and empirically optimize your model such that you minimize this loss function. In other words, you're minimizing this constrained mean squared empirical risk, right? You just plug in that function in here. If you change the loss function, you change the form of this, right? And what is that? That is how, this is your learning algorithm, right? That's what you use to assess how well you're doing and how you're going to change all your parameters in order to minimize this guy, right? That's an important ingredient in your learning process. It's something that you can set. Yeah, we didn't talk, I guess I didn't hear much about it earlier in earlier lectures, but you should be all aware that these loss functions are things that you control and you can engineer yourself. You can produce different terms and penalty terms. You can try to do different things with it. But the main point is you need a loss function for your algorithm. And the same thing is going to be true for the quantum. And there's different types of loss functions that we're going to use for that. So typical learning tasks, classification, regression, categorization or estimating a function, numerical value. And of course, next is a question, how much supervision you want during your learning? 100%, 0, somewhere in between, different ideas, unsupervised learning, self-supervised learning, semi-supervised learning, reinforcement learning, give your agent some reward for whatever it does or doesn't do well, and then, you train it this way. So there's different techniques. So what's the goal of the quantum machine learning side? It's basically a field where quantum computing meets machine learning, and it's the idea where these ideas from quantum computing can speed up and enhance machine learning algorithms, your classical machine learning algorithms, and you want it to work both on classical and quantum data. Now, is it only for the classical machine learning algorithms we know? No. It turns out we can leverage the expressiveness of quantum computing, the power of quantum computing, to develop new types of algorithms, okay, that will only make sense in the quantum, in a quantum or a hybrid quantum classical system.
So what's each of the quantum data and what kind of data can quantum data?
Oh, what's a quantum data? Yeah, okay, so think of a quantum system. Think of some kind of a spinner system, some actual atomic system, okay, that you can describe as a set of quantum states, okay? That's already, there are many types of things you can consider of quantum data. Yeah, even data in our colliders. When we produce, when we make collisions, at some point, yeah.
So basically, it just collapse.
Right, it collapsed, but you can think of it beforehand. I'm just giving you an example of a real quantum system. The whole world is a quantum system. But there are measurable quantum systems like Ising models and things like that you can already treat as quantum. Yeah. But the main point is, for the most part, we're going to look at this point, we're going to talk more about how do we improve even on classical data, right? Because the quantum part is a little bit different what you do than what you do with classical, because you don't need this encoding step. So the other direction that this goes is it goes also from machine learning to quantum computing. And this is what I mentioned, that some ideas of machine learning can be used to improve certain tasks in quantum computing. That's also very interesting. What it turns out that these can be, you can train your quantum computer as you train your neural network. Okay, you can use differential programming. In fact, by the end of our lectures, you will hopefully do that. Okay, I hope to show you that you can actually use these techniques to train these systems. Now, there are multiple ways you can combine these things together. You can use a quantum computer as a co-processor to accelerate something like training or inference. So you have your classical stuff, you have your quantum co-processor, you want the thing to go faster. The other thing that you can do is you can actually create new machine learning paradigms and models that are going to leverage quantum computing. And these are so-called quantum neural networks, quantum variational circuits. There's different types of things, for example, tensor networks, quantum kernels. And there's a very interesting connection also to kernels that we're going to talk about a little bit later today. But these are all great, right? But I don't think we have, we're going to focus mostly on the quantum neural networks in the next lectures. We're going to focus on this idea of variational circuits. It's a very powerful idea. We're going to focus on that because it becomes something rather practical. But I would like to also connect to the things you saw today. Principal variation, where does this idea come from? It actually is a probabilistic idea that comes from probabilistic machine learning, of all things. And so we're going to focus more on things that work in the near term, so-called near-term systems. So these are actual quantum computers that have, since 2019, IBM, Google, many other startups have built quantum hardware, IonQ, using different paradigms, superconducting qubits, ions and lasers and so on. And there's many different instantiations, but the main point is we're going to focus on those types of algorithms that can work on realistic quantum devices without specifying necessarily which one. We're going to abstract that out. Okay? So for this, we need something rather concrete. And what we're going to look at today and also on Thursday are so-called parametrized circuits or variational circuits. They're at the heart of this approach. What's the idea? The idea is that this is a hybrid system. It has both classical and quantum components. And they're made up of gates. It's a gate computing. So we have fixed gates, right, that we need. Also, we're going to encode our data. We have some fixed gates. And then we're going to have adjustable gates. And this is the key part for machine learning, adjustable. These are gates, quantum gates, that have parameters that we can change, adapt, as we do in a classical neural network. There's going to be variable parameters. Now, the quantum part and the classical part are going to talk to each other. So how do they talk to each other? The quantum part, we can make a measurement at some point after we have our circuit and we have our quantum gate. We can make a measurement, right? And that's going to give us a scalar, okay? Now, we're going to try to do so that this scalar represents the cost function, the loss function, something that we need to optimize and minimize. And that could be, for example, if you're doing classification, that can be, how close are you to the true label of your input data? Or if you're doing regression, how close you are in a value to this. So the main point is that's going to be kind of like a cost function or a loss function term. And we're going to use the classical part to handle optimization. And we're going to do all the things we know, which we're going to talk about, this gradient descent and so on. We're going to go ahead and use all that machinery for both the classical part and the quantum part. So we will be able to actually propagate that information to the quantum part as well and adjust those parameters. Okay, I'm going to show you some tricks that you need to do this. But your main goal is to tune these parameters and optimize the cost function, and your goal is to look for an approximate solution. So this basically looks like this. Okay, you have your quantum state, your qubits, you have some kind of a circuit over here. Okay, you're going to do some measurements. Measurements go out. You look at this becomes your cost function, and then you go ahead and you update your quantum part based on that. And you do this and you iterate as you usually do in machine learning, and you try to, reduce the error and therefore, do something useful. But that's basically the idea in a variational circuit. Questions? All right, so let's talk a little bit. We have a little bit more time left. So I want to talk a little bit about where this idea comes from and how does it connect to what you've learned a little bit earlier today. For this, we have to step back a little bit and look into probabilistic and variational machine learning methods. Now, I'm not going to go ahead and explain them since you already have had very nice presentations. The only thing is that I'm actually visually show you some of the things you saw on the board earlier from Ramon. So, but these ideas are not going to be new to you. First idea, neural networks. Okay, there's a basic representation. You've got neurons, you've got input layer, output. These basically have a transfer function. So, the information comes in, gets transferred. The function itself can be something like a sigmoid or a ReLU or whatever else. Then, you put a bunch of these, you stake these in different layers, right? And you compute forward this function. You can approximate, depending what it is. If it's a sigmoid, this can be approximated with a hyperbolic tangent. If it's something else, you do something else. In the end, it's a nested function. And you heard about, universal approximation theory that tells you that these are the functions exactly that you can use to approximate any function. So you can use this for regression, classification. Now, as you know, there are different kinds of activation functions. You have to worry about derivatives. You heard about vanishing gradients being a problem. Of course, for the basic sigmoids, sigmoids is the guy that looks like the letter S. Okay, sigmoids are biologically inspired. They were used in the 90s to some extent, still used in some places like the output neuron. But the main problem with it is actually the derivative. What happens with it at, on the sides of it, right? Because it vanishes. And that's a problem when you have to take gradients of gradients of gradients due to chain rule. They go away, you can't learn deep networks. That's a big problem, so people have gone away from those to other things. So in neural networks, the usual idea is that you're going to compute your errors, right? You look at the gradient, so you go back, you do back propagation, you look at your objective function, you take the derivative of that, gradient of that with respect to the weight, update the weight, so on, update the parameter, and off you go, and you do this, time and again is what happens. Now, gradient descent, you've heard about gradient descent. It's an important optimization algorithm that can get you to this sort of solution that minimizes the function. You measure it locally, you follow the steepest gradient, and at each point there's some hyperparameters, learning rate and momentum and all this other stuff. But the point is that your goal is to get over here in the most efficient way possible. This is part of our learning algorithm. And that's something that's still we're going to be needing and using in quantum with some adaptation that I'm going to tell you in a little bit. Now, back propagation, right? Everything goes forward. Your outputs, you go layer to layer, backward pass, gradient descent, update the weights. Very, very simple. What you can choose are these things, right? Activation function, loss function, structure of your network, batch size, all these different things, optimizers, what's the momentum, et cetera, and whatnot. Regularization, you heard about earlier today, the power of regularization. Now, we talked about sigmoids, their problem, the saturate, and of course, you can see the gradient gets too small out here and out here. So therefore, for deep neural networks, it's not the best choice, because you're not able to train very deeply. And so the modern deep learning is you want to train deeply, so you want to have more depth, but the point is that you need different activation functions such as ReLU, right, in order to overcome that problem, coupled with regularization and some other ideas, you can do this. And there's specialized architectures like convolutional, recurrent, graphs, transformers. The key thing is, of course, the regularization is one of the key parts, in addition to the right activation function. We've heard about data augmentation and dropout. In particular, dropout is a probabilistic idea, as Ramon has told you earlier, right? Visually, it looks like this. The idea is that you randomly, at each particular epoch of your training of a neural network, you're going to randomly drop some of these connections. Some of these neurons are not going to participate. They're going to be on the sideline, and you do it randomly. And in fact, as you've also heard, there is a Bayesian connection because these guys that drop out approximates something called variational inference, okay, in Bayesian neural networks. So that is one connection that we have so far. Bayesian neural networks, as you heard also yesterday, is another very nice example because these guys are stochastic. One of the first methods, and this is an idea where you introduce stochasticity into the network. What does that mean? That means your weights are not like fixed number, it's a stochastic, right, thing. So you have a probability distribution of a weight. You're not guaranteed to get an exact number out from that weight. So that's the first idea, and that is what's going to be used rather heavily in the quantum version of this. It's also a stochastic approach. So here, you train normally these guys as an ensemble, you aggregate predictions, and you saw earlier from Ramon's talk, gives you a nice uncertainty estimate. Now, okay, I'm going to skip all this. You've seen all that earlier. The main point is that computing this posterior is intractable. It's very difficult, almost impossible. So that's why you have approximate methods. You've heard about Laplace method, Markov chain, Monte Carlo. You know, there's different problems with different things. It takes too long, maybe too inaccurate. And then is the variational approach. And this variational approach approximates, that's a key idea. You're approximating that posterior and you're doing it much faster way. So normally this is what you do in MCMC. In the variational method, it's not exact, but instead of sampling it, you parametrize this. And that's exactly what we're going to do with our circuit. We're going to parametrize the circuit when we're learning this thing. And you want to learn to do inference with that. So it's basically you use things like KL divergence, as you've heard, and stochastic gradient descent to do this. And it's a very efficient way to approximate Bayesian inference. Okay, that's basically the conclusion from the other day, which turns out to be rather important for our parameterized circuits because we're going to take exactly this idea of variational inference and apply it to our quantum system. Right? And of course, this, if you want to know more about this connection, you can read the paper by Gal and Garamani 2016 to give you an insight as to why that is. All right? Now, there is one more cool thing, and that's the last thing I'm going to do, and that is so-called energy models. There's a deep connection to statistical mechanics that I want you to appreciate. Because in contrast to the models you've heard about so far, there is a class of machine learning models that don't focus on minimizing error. They focus on minimizing energy. So you define your energy, you compute the gradient of the energy, and you adjust the weight to do what? To reduce the energy. Now, you question, what is energy in this context? Well, it can have many forms. One idea is you can use this Hebbian rule. When things fire together, they wire together. It means they should be connected. You should connect things that are, firing together. So the idea is that every instance has an energy, and you can adjust your weights of your learning model to pretty much, if you're going discrimination, you want to maximize the distance in the energy space between your states. That's your goal. So you can basically use energy to do it. And there are things like Hopfield networks, which are one of the early solutions for computer vision. And the idea was that these were fully connected graphs as shown here. And the idea is that, you try to decrease, you can define an energy function that's connected to something called spin glass theory. This is for our condensed matter friends. But the idea is you want to decrease that energy function. And this was a very early idea of an energy model. And there have been others like Boltzmann machines. And Boltzmann machines are very beautiful things. It's also a fully connected network. But now, here is the cool part. Stochastic neurons. Another very nice probabilistic approach. So now you get a probability based on the Boltzmann distribution. It's drawn from a distribution. It's not something random. You draw it from a very, very specific distribution, okay, that many of you probably have seen when they studied statistical mechanics. So it looks like this. You can even have a restricted version. But anyway, the point is that the probability comes from the Boltzmann distribution, right? So you can see that you have different states of the neuron, the connection between them, you have a bias term, and now you can define a temperature of the system. And what does it mean in this context? It means that the higher the temperature, the more random the output, and vice versa. Okay? Now, you do it until you reach a thermal equilibrium. You can use these things as generative models and so on. The restrictive versions, you don't have to wait for thermal equilibrium. You can stack them in so-called deep belief networks. Here is the key part. The quantum states that we talked about, what are they? It's an open system. Because it's an open system, you got a huge ensemble of states, and therefore, the energy of those samples follows, again, this Boltzmann distribution. And again, we can define a temperature. And what does it mean to have zero temperature? It means you're at the ground state, lowest energy. Higher temperature means you're closer to a uniform probability. Okay? So there is a deep connection to statistical mechanics. So now that I've more or less, hopefully, introduced where these ideas come from, in our next lecture, we're going to continue a little bit more about how do we learn, construct these circuits, and learn. Thank you very much for your attention.
Let's thank him for the nice lecture. Open for questions.
The hybrid system, is that because we cannot make the whole system using quantum computers, or is there any other reason?
A good question. Now, quantum computers, one of the problems with near-term quantum computers. Now you can have an ideal quantum computer, but we're not going to talk about those. We're going to talk about realistic quantum computers. And realistic quantum computers, one of the key problems is decoherence, right? And if you want to get anything out of it, you have to make a measurement of sorts. And so the problem with doing this within that is that the time that it takes to do it and the operations that you need to apply, you're out of time. You basically lose coherence. You can't really do this cycle that way. But if you can abstract just that part, that's why you want to put the quantum part of this hybrid system on a quantum computer, and you want to ask it to do a very specific thing that the classical cannot do. The quantum gates that we talked about, the entangled gates and so on, they can do things that classical cannot do, and you want it to do just that, and it's just a set of a few operations which realistically you can actually instantiate on a real quantum computer with certainty, relative certainty. And you don't need, otherwise it becomes too, if you think of trying to train gradient descent and so on, and trying to do that iteratively, you basically run out of coherence and possible operations that you can do before that you lose the fidelity. Yeah, thank you. Yeah, thank you for that question.
Any other questions?
So I'm going to show you really quickly. First of all, let's open the website. Okay, you can watch this video later, but I'm just going to show you the different activities. And Machine Learning for Science currently participates in Google Summer of Code. So for many of you who are students and postdocs, this could be a very interesting opportunity for a paid internship where you're maybe working on machine learning algorithms and applications in science. We have about 22 or 23 projects this summer, very competitive. There's our very competitive selection out of hundreds and hundreds of applicants. And there are both classical and quantum projects in particle physics, astronomy, astrophysics, planetary science, you name it. So including, I forget how many, 5 or 6 quantum projects. So if you're interested in the topics that we covered in the school, classical and quantum, you're welcome to take a look. We also organize hackathons pretty much every year. There will be one later this year. So when that happens, if you're interested, in fact, this particle images challenge that I was advertising was actually, we periodically also use as one of the challenges. There's about 6-7 challenges at any given time to give you a flavor of what happens. And this coming one is going to also have a quantum machine learning challenge. So you'll have a chance to compete and maybe win some prizes and learn something in the process. All right, I'm going to come back here, and just as a very super quick thing, I want to certainly, you all know about the Large Hadron Collider, so I won't go too much into that, except I just came from there. But anyway, this is a CMS experiment. And the idea here is that we're going to use the data set, which uses one of the detectors of CMS, the electromagnetic calorimeter. You can enroll it, and then you can basically convert the energies that is recorded by this detector in the different cells into a pixel, right? Brightness, you can create images of different particles like electrons, photons, but turns out you can also do quarks and gluons and tops and everything else under the sun. But in this particular challenge, we want to separate electrons from photons without any tracking information, so just based on these images. So it's a computer vision challenge, and some of you, I guess, are working on this. And so very quickly, I want to just run through that and answer, if anybody has any questions, you can also ask during this hands-on time. So let me just quickly show you what is in this particle images notebook. In fact, just to tell you, here's the link in that slide was the link to our hands-on activity. I posted that in Slack. Hopefully all you've joined the Slack channel. I want to encourage you to ask questions there today so that instead of us helping everybody individually, everybody profits from the question and the answer. So you'll find a link to this hands-on activity, and one of them, this classical particle images, is a Jupyter notebook and Colab. It is going to open in Colab. And in fact, I have it open here. So this is the classical version, and it explains the problem. It tells you what the data set is. You can actually run this thing. You can connect it, and so on. And then you can, create the directories, download the data sets, import modules, set up some learning parameters, load the data, play around with this thing, and, define your perhaps convolutional neural network model. You can update it. You can optimize the one we give you. You can put a different one if you want to train maybe something like a ResNet or a vision transformer or whatever you want. This will go here. Then you can train it, evaluate it, and so on. So that's basically the challenge. So I just quickly go through that. And if you have questions, you can ask me. So during this activity as well. So let's go back to the slides. Again, this is going to be the GitHub link for our hands-on. So please go there. You'll be able to access all the notebooks. And the very first thing we're going to do today is the QML basics. That's pretty much the goal for today. If you finish it, continue to the next. We have more. But this is the basic one I would like everybody to do today. And so the idea is that you'll be using Penny Lane to create your first quantum gates and circuits. And you're going to build quantum nodes. And the goal is to build this Bell state that we talked about in lecture, right, from Hadamard and C0. And then there's going to be an exercise. So we'll show you how to do that and explain we let you explore a little bit how that works. And then as an exercise, we'd like you to build this GHZ state, which is going to be the 3-qubit version of the Bell state. And you'll get a chance to train this thing and optimize it as well. Now, that's the project right now. So in fact, I would like to also to introduce Tom, who I think is connected on Zoom. So Tom, are you there?
Yes, hello, can you hear me?
All right. So you're back here. So Tom is a PhD student in Munich, currently in US for something. But he and I, we prepared this tutorial for you guys. And Tom is our repeat ML4Sci Google Summer of Code, one of the Google Summer of Code students of last summer, who is also working this summer. And I'll turn it over to Tom to introduce a little bit Penny Lane and run you through the QML basics part of the notebook that we want to show you. And then you get to explore on your own. And I would suggest that maybe you work in teams, maybe the same teams as you are working on other projects. So this way you have maybe somebody else, a friend to work with. So Tom, let's turn over to you.
Yes, hi everyone. Great to be here. I hope you have a nice summer school. So as Sergey said, I would ask you to open the GitHub repository we prepared and check out the first notebook, the QML basics one. And there is a Colab link basically in the README file, and you can open it there, and then you will have to go to File and save a copy in your drive. This is important so that you can actually run it and edit it, because otherwise.
Tom, do you want to share screen or should we share it?
Sure, I can also share my screen.
Yeah, why don't you go ahead and share it? How do we project? Is there a way to?
You need to log into Zoom. I think that might be the easiest way.
Okay.
Stop sharing.
Stop sharing.
Yeah, your screen. Oh,
I'm not
no,
sharing.
you're not sharing.
No, I'm not sharing.
I'm sharing currently.
So it's in there. So, but if you log into Zoom as well.
I'm there. Oh, but as me.
No, the Slack channel. If you go to Slack channel, I posted the Zoom link over there.
Oh, okay, yeah. Just a second. We'll have it pull up here so you don't have to, twist your necks. Look back.
And you should be able to see his screen over there.
Okay, great. Without computer audio, right? Yeah.
And then you can minimize.
Yeah. Okay, great.
Got it?
Yep.
Okay, great. So yeah, this is the repository, and yeah, as I said, here we have these are basically Colab links, and I would encourage you to just use the Colab. It's the easiest. You can pull it up, and it opens the notebook basically. And as here suggested in the screenshot, you will have to go to File and Save Copy in Drive. This creates a duplicate basically for your own, because you can't edit and run this notebook because it's owned by me. But if you save a copy in your drive, you have it on your own, you can run it, you can play around with it, do whatever you want. For people who maybe there are some who don't have, for example, a Google account, there's also a folder containing the raw notebooks, so you can clone the repository, download it, run it locally on your own machine if you prefer that. But I would advise you to go with Colab. I think it's the easier one. And so yeah, we would like to ask you to start off with the QML basics one. This is this notebook here, and we will basically in this notebook explore the basics of penny lane. So how to create a circuit, how to run it, how to then create gradients and optimize a quantum machine learning program. And yeah, we're doing that in penny lane. Penny lane is a library specifically designed for quantum machine learning. So there are different other libraries for quantum computing. So for example, probably the most famous one is Qiskit from IBM. And there are libraries by Google and many more. But I personally really like penny lane because of many reasons. First of all, it's really made for quantum machine learning. You can also do classical quantum computing tasks basically for it, but the functionality for creating gradients, for optimizing circuits in penny lane is probably the most advanced from the different packages. So it's very good for quantum machine learning. And in addition, it does have a plugin system, which basically enables you to connect with actual simulators, but also actual hardware. So you can, in principle, write a program in penny lane once, then run it on a simulator, run it on an IBM machine, run it on another machine from Amazon Bracket, for example. So that's very versatile and very convenient. And in
Tom,
addition,
can you hear us?
Yes.
Yeah, can you speak up just a little bit, or maybe get a little bit closer to the mic?
I can turn my mic up a bit. Better now?
Oh, that's good. Yeah, thank you.
Yes, okay. Yeah, and as a last point, I think penny lane is also great because it's very actively maintained. So there are many people working on it. It's, I think, one of the most used quantum machine learning libraries. And so oftentimes there might appear a paper on something, and it won't take super long until someone implements it in penny lane. So yeah, also there's a very active community. So they have a forum. If you ask a question, you get an answer usually within a day, and often even from authors of papers. So I can really recommend it. And so we want to dive into this one today. And so we would like to ask you to just start off, as Sergey suggested, to just get together in groups maybe and start going through the first notebook. We will teach you just how to create circuits, how to run them. And then there are a couple of exercises in this notebook. And yeah, if you have questions, you can of course ask in the room, but probably the easiest is to ask on Slack, so we can answer them there. yeah, so go ahead and have fun. So I will stop sharing and head over to the Slack. And please don't be shy. Feel free whenever you have any questions. Also, maybe unrelated to the exercises, anything about penny learning or quantum machine learning, keep them coming.
Sorry, yeah. So basically what we're going to do is that once you're in groups, so Tom is going to be on monitoring Slack, and so will I. And I think Jack and I were going to walk around, and if you have questions, we'll try to help you. But we do encourage you to post your question. If you have a technical question or a conceptual one, post it in Slack, because maybe a bunch of other people are thinking the same thing. And then we can all answer it once. All right? So let's start. One more thing, if you look, you will notice that we also have the solutions to the QML basics notebook, but we don't encourage you to go there unless you're really, really stuck. If you are, ask a question, but you can always later have a look at the solutions. And we'll post solutions to the others eventually as well. So, but maybe try not to cheat right away. All right, so let's check in. So how many of you groups have already finished just running through the Bell state example that we gave? Not everyone? Okay. That should be fairly quick. You're just going to run. But then you can see what's going on. When you're done, the very first exercise we give you is to actually create your own circuit. So once you're done with running the Bell state example, you should try to make this, this Q note that we ask you to do. And let's maybe spend the next 10 minutes roughly on that, and then see if everybody can manage. Yeah. Okay, so maybe it's a good point to pause for a little bit, and maybe Tom, do you want to go over the solution of the first two?
Yes,
yeah.
sure.
Yeah.
So let me share my screen real quick. Okay. So yeah, let's have a look at the solutions. So in the first exercise, you should just create this circuit and draw it. And basically, what we have to do is what was shown in the notebook before. We create a device, and this time we choose 3 wires.
We don't hear you very well. Sorry. Could you speak up? Or maybe.
Yeah.
Oh, yeah, thanks.
Okay, so yeah, basically we have to choose 3 wires because this time we want to simulate 3 qubits, and yeah, we can do that by choosing 3 wires. And so with that, we define our new device and create a Q node with this new device, which I just named exercise circuit. And then we add the gates we want to have, always specifying the wires where we want to apply the gate, which is in this case Pauli X. This is the name for the X gate in Penny Lane, and the Hadamard gate and the CNOT gate. In the CNOT gate, to apply it, you just give it an array of 2 wires, where the first wire is the control wire and the second wire is the target wire. And then we return the expectation value of, again, the Pauli Z measurement. And yeah, if we draw the circuit, we basically get the same circuit, or you should get the same circuit that was given in the exercise. Yeah, this is what it looks like. Okay. Any questions so far? If not, then let me move on to the next one. Here we are supposed to create this GHC state, which is again like the Bell state, fully entangled, where we have a superposition of like just zeros and just ones, and we want to simulate it. And yeah, basically the circuit I think was already shown also in the lecture. You can create this state by adding another CNOT gate between the second and the third qubit, basically. And in this case, because, okay, we want to define the circuit, in this case, we want to have like a limited number of shots, right? So we again specify this shots argument, in this case with like 1,000 shots we want to simulate. And in order to measure this, this state in the end, you could just use like a full measurement of the whole yeah, spectrum of states, basically. So Penny Lane can give you a measurement of the full computational basis, so you get like the outcome for all states. In this case, I chose to just do a Pauli Z measurement on all the qubits to show you that you can also return multiple measurements in a single Q node. And this is what I did with the list comprehension to get a list of the measurement on all the qubits, basically. And yeah, then we can simulate this. I will just draw the circuit again real quick to show you actually what it looks like. Yeah, if we run this real quick, that is fine. And yeah, here we expect now to see the circuit with the additional CNOT gate. And yeah, then you were supposed to simulate this basically. And simulation in Pendulum is very easy because you just have to call the function basically, which you defined as your Q node, as you can see here. Yeah, okay. And now our drawing
Probably
finished. So
the trickiest part was also not forgetting to do the loop. Yeah.
for the measurement,
Yeah.
yeah, exactly. Yeah. So I did this with this list comprehension. You can also just give like a list separated like a normal array, of course, to give you all the measurements you want to have. And now we can see that, yeah, you have 3 measurements at the end of our circuit in the diagram. And yeah, then you obtain the simulation results by calling the circuit function, and that's it. And what I then did was to just plot a histogram of the sum of the measurements for every measurement we did. And basically, because we only expect zeros and ones, which in the poly-Z measurement basis is 1 and -1, right? We expect to have 3 and -3. This is exactly what we get here. And of course, we again don't have like a completely 50-50 distribution because this is probabilistic. So you will always have like yeah, only a sample of your distribution. Yeah, and that's basically it. Any questions for this part?
Thanks, Tom. So we have about 5 minutes left, but I would suggest that you try to get as far as you can. There's also another part to the exercise that has to do with optimization and gradients. I know we haven't talked yet exactly on how to do gradient descent here, and we will talk about that on Thursday, but why don't you run it and try to see it in action, and then on Thursday morning, we will talk about why that works and what's the trick for that. In the meantime, we'll come around and ask questions. Now, for those of you that are working on QML projects, we also posted the other notebooks that you can already look at if you want to go ahead and try to train a quantum neural network. On Thursday, we'll talk about how that works and so on. But if you want to go ahead, you can. Yeah. All right, thanks.